Thank you very much for joining us for the very first live recording of Totally Cooked. It's a real pleasure. Thank you for giving up your time at the end of a long week. Hopefully we can make the gap between now and dinner a little bit more entertaining and lively for you. So I'll pass to Sarah for the scripted intro, which we always get wrong.
Which we or me?
Yeah, you always get it wrong.
All right, I'll try my best this time. Today we're going up, up and away into the stratosphere. Fuck, I did it again. Today we're going up, up and away to explore the stratosphere.
It's the layer of our atmosphere between 10 kilometres and 50 kilometres above the Earth's surface.
What happens up there? It's beyond reach of most of our weather.
And it contains the ozone layer, where ultraviolet light from the sun is converted into heat.
The jet stream flows near the border between the stratosphere and the troposphere below.
The stratosphere really goes over my head.
So to help us understand it, we're joined by Professor Julie Arblaster of Monash University.
And UNSW's Dr. Martin Jucker in this very special live episode, complete with our own audience. Make some noise, people! Thank you very much. That was a lot of noise.
It's a bit of a shock, to be honest.
Kind of cheers Christian can only hope for.
Yeah.
It's you.
Oh, shit. Yep. I tried so hard and I've already failed. My name's Sarah Perkins-Kirkpatrick and I'm a Professor of Climate Science at the Australian National University in Canberra.
I'm Iain Strachan, a former journalist turned science communicator. We're members of the Australian Research Council Centre of Excellence for the Weather of the 21st Century.
And this is Totally Cooked, the Climate and Weather podcast.
She says, I tried so hard and I've already failed, with 2 medals hanging around her neck, certificates piling up.
We all know that I can't read and talk at the same time.
There's no certificate for that.
No, indeed. Today we're recording live from Launceston, Tasmania, during the 21st Century Weather's annual workshop.
And we acknowledge the Palawa people as the traditional owners of Lutruwita. And we're delighted to be joined by 2 special guests for our first ever live show. Welcome to the show, Julie.
Thank you. Great to be here.
Thanks for joining us. And welcome also to Martin.
Thanks for having me.
Sarah, it's over to you.
Okay, so Julie, you get the first question. What is the stratosphere?
Ooh, good question. So yeah, the stratosphere is this layer, as you were saying, high up in the atmosphere. So it differs depending where you are on the Earth. So in the tropics, it's a bit higher where it starts at maybe 18 kilometres. And in the poles, it's closer to 10 kilometres where it starts. And it's this layer that's really stable. It contains the ozone layer, which is why it's stable. That ozone kind of absorbs heat and makes it very stable. There's no weather really up there, but it can be really influential on our climate. So it's really important that we understand how it affects the weather down below.
I wrote this run sheet quite a long time ago now, and when I printed it out this morning at the hotel desk, I was reading it through again. I was like, does it contain the ozone layer? Is that a hallucination? So I spent some of the morning session today checking that, and I was like, I think it does, yeah.
Is that what AI told you?
AI from NASA says it does. So,
okay.
So I have a follow-up question, Julie. Is the stratosphere hot or cold?
Well, one of the features of the stratosphere is that the temperatures increase as you go up. And that's really different from the troposphere, which is the layer between the surface and the stratosphere, where the temperatures decrease with height. But yeah, it is still pretty cold up there. So we were talking maybe over Antarctica can be minus 80 up there. But it can have some large fluctuations in temperature still.
I might put a question to you now, Martin, which is there weather as we know it in the stratosphere?
No, there's not. So I think the big difference is because when you go up in the atmosphere, as it gets colder and colder, you're removing all of that moisture. And then moisture comes from the surface. So there's no source of moisture anymore up there. So that means it's very dry. And so anything we would call weather, as in clouds and thunderstorms and rain, just doesn't happen. It's all just blue skies.
Sounds a bit lovely and also boring.
Sounds bloody freezing. So if there's no weather up there then, how does it influence weather on the surface or closer to the surface?
There is no weather in that sense, but there's still stuff happening.
Okay.
So there's just stuff happening we can't see. There's atmospheric waves and everything, and there's winds, and how does it influence the surface is actually what we're still trying to find out. We just kind of know it does, and
So is it like a educated guess or a hunch?
Yeah. So there are educated guesses.
Yeah,
yes.
okay.
So it's like these waves. So how it works? They transport energy from the surface into the stratosphere and then back. It's a bit like phones, I guess, where you have waves between the phones. You don't see them, but they transport whatever you say to whatever Iain says, right, in terms of energy. And then once they change the stratosphere, that can then go back and influence where it came from. So that would be Iain's answer to you, which would influence how you react.
There is always a reaction.
Do planes fly in the stratosphere? Is that where they go?
Well, the Concorde used to fly in the stratosphere, but there was some issues with that because it did start to maybe have some impacts on the ozone destruction. And so, yeah, the planes fly pretty high up, as close to the stratosphere as they can, but to get the strongest winds. But I'm pretty sure they don't fly in the stratosphere. Is that true, Martin, would you say?
I actually would have said yes,
you would have
but
said
it's
yes.
really,
Okay.
really
Low,
just
yeah.
because the thing is when you fly, it's always blue skies. Once you're really up at cruising altitude, there's never any clouds. But yes, there is a bit of space between the top of the clouds and the tropopause. So maybe they're just there,
Just
but
on
it's
the
close
tropopause.
enough, I think. At least from the plane, you can see the stratosphere, let's say it that way.
What about specifically the Qantas flight from Perth to Paris? Does it fly?
So
Doesn't fly.
for everyone at home and most people in the room, we've just found out we're not flying to Paris for the
Aw.
IPCC meeting on Monday.
It's like Home Alone.
It's, yeah, I do, like on reflection, I do think this flight has a habit of being cancelled a lot. So yeah, no stratospheric viewing for us, at least not at the moment.
That's a shame.
I want to ask Julie though, what was the impact of the Concorde on the ozone layer? Like what exactly did flying through it do to it?
Yeah, so the stratosphere contains pretty much all of, or I think 90% of the ozone in the atmosphere. And so when you have some particles that are in the stratosphere that can chemically react, they can destroy ozone. And so the Concorde had, I guess, caused clouds to form in the stratosphere that aren't normally there, and those particles can then accelerate ozone
So it's
chemistry reactions.
The moisture in the clouds then disrupted how the ozone behaved, and that, led to degradation. Right, interesting.
Got a few younger members of the centre in the audience. Does anyone not know what Concorde is?
Oh.
That's
I feel
okay.
old.
Was it a supersonic passenger plane?
Was it Mach 3?
Something like that, yeah. Joint initiative of British Airways and Air France in the 60s, 70s, 80s and 90s.
Doomed for failure. It was too expensive.
Too expensive, yep.
And destroyed.
Too
that
noisy as well, I
atmosphere.
thought, right?
Yeah, it was very noisy.
I'd like to ask someone, and feel free to fight over it, about sudden stratospheric warming and their various knock-on effects. Can you explain to our audience what that is, please?
Can we call them SSWs?
No, you can't. Acronyms are banned
No
on Totally Cooked.
acronyms. But I did just say IPCC though, so. But no, SSW doesn't roll off the tongue.
It was where I had my first job, though. A supermarket in my hometown was called SSW. But
It was meant to be.
Is that true?
it's true.
Oh, okay. So you pointed to me, so I should explain. Yeah, so in a way what I explained before, the waves going back and forth. So if you have a lot of them, you have a lot of energy that can be deposited in the stratosphere, and that creates heat, if you like. You can deposit heat, and that can warm up the stratosphere, hence the warming part of sudden stratospheric warming. Then there's the sudden part, which is that this often happens very quickly. So it's also kind of difficult to predict, right? So that's the sudden part, and it's in the stratosphere. So there you go. So
Why does it happen quickly?
yeah, because these waves are strong. When it does happen, it has to be strong because so it's very strong winds as well, which you have to slow down. We actually didn't mention that there were strong winds yet, right? So maybe a very important ingredient that we haven't mentioned so far is that it's not just cold, but over the poles, it's colder than anywhere else. So we have a temperature gradient between how cold it is over the pole and warmer elsewhere, and that creates strong winds, that circle, and that's what we call the polar vortex. And maybe also important to note that the media has picked up the term polar vortex for something that is not the polar vortex.
They love
If
a
you want
good
to go off
buzzword.
on a tangent.
Yeah.
But anyway, so sudden stratospheric warming would be when that polar vortex ceases to exist in its strongest case.
I mean, I welcome that digression or tangent.
Yes.
What does the media think a polar vortex is, and what is it actually?
Yeah, so feel free to jump in as well. But what often is the news as polar vortex is the cold air in the troposphere, which is poleward in both hemispheres, poleward of the jet stream, which you mentioned in the introduction. And that's the jet stream separates the cold polar air from the warmer tropical latitude air. And so every now and then, when the jet stream wobbles, that means that this polar air can come, and that's cold air outbreak. And so that's what the media often calls the polar vortex. And I think some of the confusion comes from the fact that the actual polar vortex influences these cold air outbreaks.
Yeah.
So there is a link, and we as stratospheric scientists make the link between polar vortex and cold air outbreaks, so the media ran with it, but with the wrong thing.
With my journalist hat on as well, polar vortex sounds really cool. So
it does, doesn't it?
Yeah.
I've actually noticed, I don't know if this happens to anyone else or if it just shows how nerdy I am, but my social media feed is full of like non-verified forecasters giving updates from, free meteorological data. And they're constantly now still talking about the southern stratospheric warming and its influence actually over this part of Australia, over Tasmania and Victoria, and how it's still quite cold and there's these cold air outbreaks happening. Is that actually happening? Is that a reasonable link, or is that they're just making crap up?
Yeah, well, so we did have one of these sudden stratospheric warmings that occurred in September. And so I guess, with this polar vortex, it's got this seasonality, right? So it kind of forms in April, high up, maybe in the mesosphere. And then it kind of comes down, it moves sort of down into the stratosphere and poleward, really strong in winter, and then actually breaks down in our springtime. And so when we get these sudden warmings, they're often sort of late spring, just when it's kind of, so it kind of breaks down a bit earlier than usual. So we often get them in this kind of September time of period. And so one of them happened, in September. It was exciting. They don't happen very often in the southern hemisphere. They happen a lot in the northern hemisphere. And if we look now at, say, the October rainfall average, it looks like that pattern that came then down into the weather, into the near the surface, looks very much like it was influenced by the polar vortex breakdown. Yeah.
So then how long does the influence last for? So it sounds like it's at least a month. Is it a few months? Should we expect an influence from these events for 6 months, a year? Does anyone know?
Seasonal, right? So
okay.
It's actually one of the main interests for us to look at this is seasonal forecasts.
Yeah.
So you can gain more information when you know one is happening.
Yeah.
And it's been shown, mainly in the northern hemisphere because they happen more often, but been shown once one happens, it's difficult to predict, but once one happens, your seasonal forecasting skill is improved.
Yeah.
So it's, we might expect an effect all through summer.
Right. Understood. Okay.
Yeah, and so the pattern of rainfall, if we have these sudden stratospheric warmings, which is a weakening of the polar vortex, it's a negative southern annular mode, if we want to thinking about the more troposphere, is kind of wetter conditions in western Tasmania and drier conditions in the sort of New South Wales, Queensland area. Yeah. And then Victoria, it's a little bit kind of in between. And that's certainly what has happened. But the interesting thing about this season is that we also had some tropical influences that were kind of pushing against what that pattern was. And so it's this tug of war between the Indian Ocean dipole, which was negative, which would have been more wet over the whole of eastern Australia. And that's, I think, what the seasonal forecast was kind of thinking was going to win. But it seems like, looking back, and maybe the end of spring is not here yet.
Go stratosphere.
Yeah, but the stratosphere might have won. It's certainly in Queensland and New South Wales.
So you did say earlier that we don't get these events very often. How often do they occur in the southern hemisphere compared to the northern hemisphere?
Well, Martin is actually defining how we define these sudden stratospheric warmings.
Tell us more.
So one problem is all of our definitions are from the northern hemisphere.
Right, okay.
And so the most popular one, which is that these strong winds, the polar vortex actually breaks down. And then with that definition, we only have one single event in the entire record.
Oh, okay.
And that was in 2002.
Oh, but we've had more since then, haven't we?
Yes. So the thing is, that was a surprise for scientists. Yep. It was like, oh, wait a minute, this can happen in the southern hemisphere? Wow. And then 2019 was really the next one where I think everybody now agrees this should be called a southern stratospheric warming.
Yeah.
Even though it did not satisfy this definition.
Okay.
And so again, it was a surprise. It was like, okay, there has never been one till 2002. Then suddenly 17 years later, there's another one happening, which we need a new definition for because the one we usually use doesn't work. So that's where my current work comes in, trying to define what should we call a southern stratospheric warming in the southern hemisphere, because most of the research is done in the northern hemisphere, so it's and conditions are just different. So what is also interesting, at the same time after this 2019, we've also done a study how often should we expect this, and we found about one every 22 years, which is consistent with our observations. But we also found we won't see another one any time in our lifetimes again because of climate change. And now here we are, and there's been one last year, there's been
6
one this year.
years.
So
Yeah.
it's really interesting.
Oh, so there was one last year too.
There was one last
I
year
didn't
too,
know that.
but which, we can discuss whether it had a surface impact or not, because it happened much earlier. It happened in August.
Winter, July.
Yeah.
August.
So they don't
July, even late
July.
July. Yeah.
So they don't always have an impact on the weather. It's
No,
the timing of the
timing
year.
is-
Yeah.
yes,
Okay. I
yes.
didn't know
And
that.
even in the Northern Hemisphere, it's not always, and that's part of the research that people still do, is which ones have an impact and which ones don't.
Yeah.
And we don't really know yet.
Okay. So they're very unpredictable.
Yeah. And even if they happen, you don't know whether they're actually going to have an impact or not.
Oh, that's a bit.
But they
annoying.
are, but they are a source of skill if you do
Yes,
have them.
but-
Yeah. If you get it.
If you get them, if you can even get skill from June. If you see one forming in the stratosphere high up, you can have skillful influence on the predictions for spring.
So they might be happening a lot more often than what we've been able to define.
Yes, I mean, that's one of the reasons why we try to find another definition. And what we have done so far, you can reveal some big reveal.
Oh, yes. Please tell us more. Yep.
So, we think at least there are about 12 interesting events since 79. Yes, but more to be
determined.
discovered. Yes.
Read your paper once it's published.
Exactly.
Yeah.
Yes.
But I do think part of the reason why we think they're happening more often is that we've started defining them, and work led by Dr. Unpal Lim at the Bureau of Meteorology has really found sort of relationships between these weakenings, not sort of warmings necessarily.
Right.
So we're talking about them more because the research is really accelerating into it as well.
So bottom line, they behave a bit differently in the Southern Hemisphere compared to the Northern Hemisphere. So we can't necessarily adapt that science to our weather because it is different.
Just a bit more laid back, a bit more charming in the Southern
more
Hemisphere,
chill.
a bit more chill. Yeah.
Very chill.
Yeah.
Very chill.
Southern stratospheric warming. I want to ask about polar stratospheric clouds. I read about this in my research. I don't know what they are, but they sound cool. Are they a thing? Can you talk about them, Julie or Martin?
They're very pretty. I've never seen them. Has anyone in the audience seen them?
Only
a Northern
shout
Hemisphere
out to Thomas Spengler in the audience.
Well done.
Were you on the Concorde when you saw them?
He created them.
Oh, right.
So it's not my area completely, but you get these polar stratospheric clouds forming when it's really cold over Antarctica in the winter time. And the reason we care about them is that they can accelerate, again, ozone depletion, because they give these surfaces to accelerate that chemical reaction. And so, you get the ozone hole over Antarctica still forms every year in the spring, and it forms in spring because you need both sunlight and these polar stratospheric clouds to really accelerate that ozone depletion.
Do they form when it's particularly cold? Is that
Yes.
the process?
Yes.
Yeah.
Yeah, because the main thing is not water clouds, right? It's what is it?
Ice
Ammonium,
cloud.
ice, something like that. It's
Ammonium.
not normal. Something. It's
Chemical
there's
ice
nitrogen
clouds.
in it, right?
That sounds dangerous.
Well, nobody lives there.
No, that's
it's
true.
okay.
Penguins,
Penguins? No, not in the stratosphere.
Not in the stratosphere.
Yeah, no.
Have we taught you nothing?
unless they're in.
But that actually is another
Concorde.
thing. That is another thing. The last time I talked about this southern stratospheric warming at the ABC, what they were showing while I was talking was penguins, and I tried to tell them, no, it's not. But whatever.
Well, cold penguins,
Yeah.
Antarctica.
Antarctica.
Yeah, that's all they've got.
You
Yeah.
gotta show penguins.
You scientists always want it to be accurate, you know? Always want it to be correct.
At least in the ballpark would be helpful.
Well, yeah, penguins on the ground, clouds above the penguins. So perfectly editorially justifiable, I
that
think.
rain ammonia.
Yeah. Acid ice is killing our penguins.
Faster than climate change. All right. Maybe I'll stop there.
Okay, I'm going to pivot to a slightly
Penguins on
more
acid?
Pardon?
Penguins on acid?
acid penguins. Well, we are getting high. Does the location of the stratosphere or its distance to the surface change depending on where you are on the planet?
Yes, I think that's what Julie.
Yes, so in the tropics, because the tropics are a lot warmer, the weather kind of goes much higher, and so you don't get to the stratosphere until about 18 kilometres, where you start having that lack of weather. Whereas at the poles, it's colder, we don't have as much weather, and so the stratosphere starts at around 8 or 9 kilometres high.
You already said that.
Yeah.
Yeah,
That's
thanks. It was on the run sheet.
Doesn't always help to follow the run sheet.
Can we talk a bit more about the ozone layer, please? Why is it in the stratosphere and why is it so important?
Yeah, okay. You've been working on the ozone assessment. I think you should take that one.
Yeah, so it's in the stratosphere because it a reaction of UV with oxygen and
What's UV?
Ultraviolet radiation. So the ultraviolet radiation is coming in from the sun, hits the atmosphere, and then it has this reaction of ozone molecules. They kind of combine and form these. Oxygen molecules combine and form this ozone. And then I guess because a lot of the ozone forms and then it blocks all the UV, and so then it saves us down at the surface.
From being frazzled. Yep.
Yeah.
Like Sarah.
I'm always frazzled.
Yeah.
Have I had too much UV?
There is also ozone. So ozone in the stratosphere is the good ozone. It's the one that protects us. The ozone also forms in the near the surface from cars, from pollution, and that's harmful to us. And so, there's good ozone and there's bad ozone.
Okay. What is the status of the hole in the ozone layer? Something that we were all very worried about in the 90s, I think.
Should we still be worried about it?
I think we need to be mindful of it, is what I would say. So the ozone is, a good news story. We controlled for the substances that destroy the ozone layer, the chlorofluorocarbons and other compounds that were used in refrigerants and air conditioning. So the Montreal Protocol was signed in 1987, and you can see that the production of those CFCs and other compounds that destroy ozone really started dropping and were pretty much controlled for pretty quickly. But there is still, of course, some. They have a really long lifetime in the atmosphere, so there's still some in the atmosphere. So we still get this ozone hole forming every year over Antarctica, but it is starting to recover. Yeah, it's not getting worse.
It's a good story, good news story.
Yeah, but I think it is important to note that it's still there, right? It's not gone yet, and a lot of people are surprised. It's kind of solved, but it's still there.
Yeah, and we don't expect it to get back to sort of 1980 levels until the 2050s, say. And I guess the interesting thing in recent years is there's been really, it's not getting worse, but it's been 1 year there's a huge ozone hole, 1 year there's a really small ozone hole. Like this year, a good aspect of the sudden warming is that over in the stratosphere over Antarctica, it was really warm, so you didn't get as much ozone destruction. And so it's a small ozone hole this year.
Was there always a naturally occurring hole in the ozone layer, or is it entirely man-made feature of the Earth system?
Well, that would require having measurements going a long way back, but we do know that, the ozone destruction did start at the same time as the use of CFCs, I would say, but I think ideally we'd have measurements further back.
And without human-made components, there is an equilibrium as well, right? So the human-made components, they destroyed the equilibrium. And
So what would have happened then if we didn't have the Montreal Protocol? Where would we be, and where would we be heading with the ozone layer?
Well, we've done experiments with our models, our climate models, and they're called world-avoided experiments. And you see, ozone, the kind of ozone hole, or I guess ozone depletion over, say, Melbourne getting quite severe if we hadn't controlled for that. So
Would have it been like a global effect because it is concentrated to the southern hemisphere? Would that have spread to other parts of the world as well, or would it have just been concentrated where we are?
You have ozone depletion even in Melbourne. You see it. Yeah. So no, there is a signal globally from these CFCs, but it's much larger in the polar regions, and particularly Antarctica where it's really cold and you have these polar stratospheric clouds that accelerate things.
maybe also at world avoided, CFCs also are greenhouse gases.
Yes.
So I think we've also removed about the degree of warming thanks to phasing them out.
Really? A degree from
I think so.
Yeah, right.
Or is that too much? Maybe it's well. I think it was locally.
Yeah,
at some
I think in
places
the
a
Arctic,
degree.
yeah.
Yes, right. Yeah.
So that's a lesson, right?
Yeah, it's actually the Montreal Protocol has done a lot more for reducing the global warming than the Kyoto Protocol or the Paris Agreement, you could say.
Well, that's, it's pretty, the Paris Agreement is coming up to 10 years in a few weeks. And yet, safe to say, it hasn't done a lot, but it just goes to show that some of these agreements do work if we really put our minds to it.
Why was the Montreal Protocol so much more effective and successful than some of our other attempts to reduce emissions?
I think it was about our health, immediate impact, right? You could feel it that year that it was signed. There was more UV radiation. So I think there was just an immediate effect.
I think also the industry got really on board with it. Industry, they had something else ready to swap in to air conditioners and refrigerants, and they were, I think it took a lot of leadership from the scientific community, and decision makers and industry leaders were also really engaged in solving the problem.
but there was a simple fix or an easy-ish thing to swap out,
relatively
simple.
as opposed to, say,
Telling everyone.
oil and gas.
Yeah.
Yeah.
Yeah, people could continue buying fridges, right? It was not that, no, don't buy a fridge because you...
But I will say, so one of the interesting things with the Montreal Protocol is it's like the Paris Agreement, like you can have amendments, right, to strengthen things. And a few years ago, they saw that the CFCs actually were starting to increase again. Like there was more emissions, and they were able to track it down to which region of the world was making these CFCs, and that international kind of, I guess, the fact that people could see that they were making them meant they stopped doing it again. So you have to really, even though it's a solved problem, you have to really keep
Name
on
and
top of it
shame.
and monitor the CFCs, monitor the ozone to make sure that it's still on top of that.
That's interesting, though, that you can track it. It's an immediate effect. And I think that's another issue with climate change and things like the Paris Agreement. It's going to be years, hundreds of years until we even notice anything, if anything at all. So it's a bit more hard for people to grasp. It's not as tangible that, if you make change now, the change won't be immediate for climate change, where it was for the ozone layer.
Well, this was more about the emissions, I guess, of the CFCs, yeah. But yeah, there's also right now they're a bit worried about rockets. There's a lot of more rockets going up and space travel.
Right.
And so thinking of all the things that, or new compounds that are being created for new technology that we need to make sure we're monitoring. So
I don't know if anyone else who maybe my age or older remembers getting a fridge and having like a CFC free sticker on it. Did anyone else in the room get those? And I was a kid at the time, and felt very smug and very impressed that we were no longer contributing to the ozone hole, but we still very much had to slap as we walked out the front door.
That's set you on your path to electric vehicle and solar panel
Absolutely,
ownership and elite
Just
level
feeling more
smugness.
smug.
Just as a quick aside, which won't make it into the edit unless I'm feeling very lazy, Zach's given me a discreet little speak up signal. So I think probably you two are okay, but Julie and I are in the quiet corner, so we will...
naughty.
The naughty and the naughty quiet corner. Okay, be louder.
We're not naughty.
They'll be loud.
So we've spoken a lot about CFCs, but Martin, I think I'm right in saying that other things can get into the stratosphere and hang around for quite a while.
Yes.
And I'm thinking primarily here of volcanic eruptions, which I believe you might have been looking into a little bit in the last couple of years.
Yes, correct.
Can you tell us about volcanoes and the stratosphere, please?
Yes. So, there's the general volcano, which puts up all this stuff in the smoke, right? And all of that, it's very powerful, so it can put it up very high. And that can reach the stratosphere. And in particular, if it's close to the equator, to the tropics, that's where most of the air actually enters the stratosphere. And if you have tropical volcanoes, then all of that matter can be spread out globally over through the stratosphere. And what's particularly important there is sulfur, because that can reflect solar radiation. So you can use it to increase the albedo, so how much of the solar radiation comes in gets reflected right back before it can actually heat up the surface. And so the main impact of these volcanoes is global cooling for a while.
How long is a while?
It can be years, I think, right? Yeah.
Yeah.
Year, two,
Does
something
it
like that?
Depend on the size of the
Yes,
blast?
definitely does.
Okay.
Yes, because all of this matter. As in the stratosphere, there's no rain, so it cannot just easily rain out.
Acid rain.
Acid rain. Yeah. What would happen if with all the stuff that remains in the troposphere? But it's got mass, so it will still
It'll fall out eventually. Yeah.
Yeah. But then there's this special volcano that I've been working on, which is the Hungatonga Ha'apai volcano that erupted in January 2022. And it was very different there is that it was underwater, but not too much underwater, and it was very powerful. So it managed to basically evaporate all the seawater that was above it and send it all the way into the stratosphere. And that was very different because instead of reflecting the sunlight and then we would expect the cooling, water vapor is a greenhouse gas. So the question was, well, what is happening now? And there's people try to put it into perspective. It's like 20,000 Olympic swimming pools.
Yeah, right.
I still can't imagine how much that is. But
do you just line them up or does it go around? Or
you just swim through all of them.
Oh, God.
And you know how much it is.
Yeah.
Yeah, so it was a massive amount of water vapor that got into the stratosphere. The stratosphere generally being very dry, it did make a big difference. So the question was, are we actually going to see a warming because of that now, because it's a greenhouse gas? How long is it going to be, and all of that?
Would that extra moisture put into the stratosphere affected the ozone layer?
Yes,
Could that have been some of the reason why it degraded recently quite fast, maybe?
So yeah,
This is a research question.
so what simulations of these, when you use big climate models which do all the ozone hole chemistry and everything, if you put that volcano in there, what you see is a larger ozone hole, not immediately but the year after. So that would be 2023, 24. And we did indeed see a larger than normal ozone hole. And what's also interesting is that, as Julie explained, we expect this polar vortex to influence the southern annular mode. And that summer was an El Nino summer, and people expected dry and hot.
Yes, that's
and
right.
it
I
was
remember.
really wet.
That screwed up everyone who
Exactly.
does science comms
Yes.
in the climate space.
Yes,
Yep.
that's right. And then there were these stories of the farmers selling off their cattle and then
Blaming the Bureau of Meteorology.
exactly blaming the
incorrectly, might
Bureau
add,
of
but yes.
Meteorology. Poor bastards.
Yeah.
And and it all works very nicely with this volcano story, because
Interesting.
that's exactly
Yeah.
what you expect if you look at what the volcano did to the polar vortex.
Interesting. So that caused or at least contributed to...
Yes, so you would have the southern annular mode, which would suddenly be in the other phase than what you would expect in an El Nino,
Yeah.
and you would get a wetter than usual summer.
Yep. That's
And-
exactly what
And
we had.
did it affect the southern annular mode because so much water entered the stratosphere and it changed the normal
Yes.
parameters?
So more water, more polar stratospheric clouds,
Yep.
therefore more ozone depletion. Yes.
Interesting. I never knew how it all linked in together in quite that way.
Did anyone see that volcano erupt? Like, was anyone on a boat near it?
Well,
The
there's people
satellite
living there.
did.
What? There was people living.
Well, yeah, it's an island. Not
But
the
was-
island itself of the volcano, but close enough. They had
Oh.
huge tsunamis and everything, so it was.
Are they okay?
Well, there are people who weren't okay. No.
Okay.
So no, there was a tsunami warning, and there's a lot of, actually, the first research I got across was people studying the shockwave, the atmospheric shockwave.
Oh, I saw image.
Yeah,
This
it
was
went
incredible.
It went twice around the globe.
Yep.
And there's like a paper of somebody in I think Reading reading off
Yes.
and they could see the spike twice
Yep.
in the pressure. So
Yep.
that's on the other side of the globe.
Yeah, that's incredible.
Pretty impressive things. Yeah.
Have we had volcanoes do this before? Or is this the first one that's put
Yeah.
so much water vapor into the atmosphere? The
There's a-
stratosphere.
First one we've observed, I think.
Exactly.
Yeah,
So
exactly.
which is why it was so interesting. Right?
Yeah.
We had no idea what was going to happen. And yeah.
So how long is it going to influence our weather for?
Good
Is that
question.
the $1 million question?
Yeah, it kind of is. Yes. So I think
Yeah. What's your educated
till
guess?
the end of the decade.
Oh, okay.
But our simulations were kind of limited.
Yeah, okay.
So, it's still out there. And I have to say, there's so many other things happening at the moment in the climate that we did not have in our study.
Yeah, right.
So it's very easily overwritten by, things like the hot ocean temperatures. We
Yeah.
didn't have them. We set it to climatological, so normal.
Yeah. So
Ocean
you
temperatures
cancelled
and
out all
everything.
other things
Exactly.
other than
We
the
had
volcano.
only the water vapor
Yeah.
from that volcano, and everything else was to normal,
Yeah, okay.
which is not at all the case.
Yeah. There's
right
so many
now.
things going on at any one time.
Yes, correct.
Hunga Tonga is an interesting case in that it's a lot of water vapor sent into
Yeah.
the stratosphere. What about other large volcanoes that erupt and emit other kinds of matter? Does that reach the stratosphere? And if it does, what kind of impact does that have on our weather and climate?
Yeah, so Martin was talking about sulfur. A lot of volcanoes have a lot of sulfur that then leads to these sulfate aerosols in the stratosphere. And they can also be surfaces for ozone destruction, so influencing the stratosphere in that way, as well as just through the radiation of reflecting sunlight. And there are studies that have shown, yes, lots of influence of even small volcanoes on the ozone hole. But yeah, also I guess the where the volcanoes are and what they're putting up into the atmosphere is the key to knowing if it'll affect our weather.
We've seen quite a bit during our annual workshop here in Launceston, reports and research on the 2019-20 bushfires. And I remember, I think, reading at the time that a lot of smoke from those fires reached the stratosphere. Can you tell us a little bit about what the impacts of bushfires are on the stratosphere and then subsequently on our weather and climate?
Yeah, so that was a similar thing again, it was not the same year that it would have impacted the stratosphere, but the year after, because it just takes so long for anything to get there. And it's a similar story. It's similar to the Concorde. So you suddenly have more of these particles in the stratosphere where the chemistry, for ozone destruction, they can congregate and have a party. And,
is it a party that we want to be at with all the sulfur and ammonia?
It's 420, right?
Oh,
Let's go have some ozone.
Yeah, right.
Yes. So you get more of this ozone destruction chemistry going the year after.
Yeah, so I think when we were saying, has the ozone hole recovered, we've had these real kind of swings from big ozone holes to small. And part of that is we've had these big kind of crazy events like the Australian bushfires. Really punched a huge amount of smoke into the stratosphere. And then Hungatong is this really unusual volcano. So that could explain part of those swings, but it's also could just be internal variability or maybe some other climate change thing. Who knows?
Sarah, have you made it to studying the stratosphere on your run sheet? I think it's
no, I'm at asteroids.
Do you want to ask about asteroids?
Yeah.
Stratospheric asteroids?
I'm kind of stumped because it's not a question that I was expecting. It just says, and what about asteroids? Which seems like a bit of a
what
swing.
about them?
You've done your background research.
What
about comets?
Well, yeah, maybe about comets too. Do they come into the stratosphere?
Is the question whether they have a stratosphere?
It says here, due to the lack of vertical convection in the stratosphere,
yes,
materials that get into the stratosphere can stay there for long times. That's
Yes.
great English. Large volcanic eruptions and major meteorite impacts can fling aerosol particles into the stratosphere, where they may linger for months or years.
Yes.
So
is this asteroids coming to Earth
Yeah.
I thought it was the other way around, like asteroids actually passing through all layers of the atmosphere. No?
either or.
Do you guys know anything
Well,
about
I guess
this?
if you have a huge meteorite impact that would, put up anything that was there before they impacted, puts that up in the stratosphere, I guess you could have similar effects. Yeah.
How likely is this to happen in our lifetime? Do your models predict this?
Should we do a second day after tomorrow? Or?
Oh, yeah. Yeah, we've talked about this.
Yeah,
It
I
should be
know.
like the year after tomorrow or something. Yeah.
Yeah, I don't know. I mean, there are theories, right, with the dinosaurs that went extinct, because of global dimming. I guess that would be a similar effect to the volcanoes, yeah?
And it would be the stratosphere that would be affected.
Yeah, because anything that's in the troposphere would get rained out pretty quickly. So everything that stays would be in the stratosphere.
How long could it hang around there for? So
Depends how heavy they
you know
are.
a lot about asteroids.
Thank
No.
you.
If there's
I
any
think
Martians on them or not.
But what I might say, not as long as the water vapor, because all of these things are heavier.
Yeah. Okay, that's fair enough. All right.
Hungatonga 1, meteorite.
Yeah.
I think we're more likely to have another underwater volcano than we are to have an asteroid
Yes.
hit Earth and kill us all.
Especially we have nukes, right, for the asteroids.
Oh, yeah, that'll save us. It's just like, don't look up all over again. I want to kind of go back to the southern stratospheric warming a bit because we had one in 2019. I think we briefly touched on that, but that seemed to have an opposite effect to the weather that we've had with the most recent one. Was that because of other drivers as well? It was a very hot and dry summer here in Australia, or hot and dry spring, I should say.
Yeah, but we have had a hot and dry spring over New South Wales and Queensland.
Right,
So
okay,
it
so
is
that's it, yes.
similar,
All
but
right.
I guess
It's similar in that way.
Victoria
Okay.
has been maybe a bit different to 2019
Right,
in that
understand.
it was...
Okay.
Of course, Victoria is a bit different.
Yeah, and so I guess one of the differences this year is that we've got the opposite sign in the Indian Ocean going on. So it's it's not, they're not kind of getting together and causing dry conditions. They're kind of fighting it out. And
Well, we were in a drought then as well, weren't we? Okay, we were in drought for a couple of years.
Yeah.
Okay, so it was kind of like part of the mix,
Yeah.
not the whole story.
Yeah.
So now I'm at studying the stratosphere, Iain. Oh, yeah, it's me, sorry. But
Slick.
it was you again.
Slick.
That's why you were
Not
leading me there. Now I get it. Okay, so Julie, can you tell us how scientists study the stratosphere?
Ooh. Yeah, so we, I guess, don't have as many observations in the stratosphere because it's, our weather, like stations don't really measure that high up, but we do have some balloons that go up there and measure the temperatures and winds and things. We do like to use climate models to try and understand some of the interactions. And I guess there's, a lot of research at the moment into seasonal prediction because we do see it as this additional kind of way that we can get some extra skill in predicting the season ahead. And so a lot of the science around the stratosphere at the moment is around these southern stratospheric warmings and how we can use them to get better skillful predictions of rainfall and temperatures for agriculture and other seasonal things. Yeah.
Okay. So in the notes here, it's got satellites and LiDAR. Are you able to explain how they might help and what the difference is? Because I've heard of LiDAR before, but I don't actually know a lot about it. Or maybe one of you.
Well, one thing, I think an obvious thing about satellites is, I mean, Julie's touched on it. It's nobody lives in the stratosphere, so you can't have an actual physical station there to measure stuff.
Why? Why hasn't Elon Musk invented a way to do this?
So satellites, of course, are then the obvious solution because they look from the top and can look at the stratosphere.
So they sit above the stratosphere.
Yes, yeah, they do sit above the stratosphere. Yes, and LiDAR.
Neither of them about LiDAR.
Does anyone know what that stands for?
Does anyone in the audience
The L
know?
is for laser, right? No?
Laser radar.
Oh, it's a
Laser radar.
Is it an instrument on a satellite?
You can be a satellite.
Instrument. Yeah.
But I think that's what MLS is, isn't the L, the LiDAR?
So
Yeah,
we've had some really good satellite measurements in the last few decades that have really accelerated our understanding. But those satellite missions are kind of already beyond their lifetime, and there's no plans to launch new ones at the moment. And so stratospheric scientists are quite worried. Something like Hunga maybe in a few years we won't have the instruments on satellites that will be able to actually measure the impacts of that. And so satellites are crucial for our understanding of the stratosphere. There was a project a few years ago called Google Loon that was going to put instruments on. They were going to launch lots of little weather balloons that stayed in the stratosphere for internet. Yeah, called Google Loon. And
sorry, what was it called?
Google Loon.
Loon.
Loon, as in lunatic.
As in
lunatic.
as in loons on Golden Pond. Yeah.
Didn't know loon was moon in French.
And so they came to one of our conferences and we're excited to maybe get some extra measurements, but I think it didn't last. It was hard to get the airspace control, I think, was the problem. Yeah.
Well, I think it was also just before these microsatellites became viable. So I think it was just, compared to that, it's too expensive, I think.
Yeah, okay. So with weather balloons, how far can they go up? You said that they're useful. How far do they go up?
I know about the ozone sondes. They go up to 50 kilometres or something.
Yeah, right.
Yeah, but
I think a normal weather balloon is only about 20, 25.
But that's still quite high.
It's still quite high, but it's not. Yeah, it's only, you can only just in the stratosphere.
And so how long?
Yeah.
Like how long is their trip? How many hours do they last? Sorry, maybe I shouldn't go down this particular tangent.
We're modelers.
Okay.
Yeah.
Who use observations very thankfully, gratefully.
What are the biggest unknowns in stratosphere research?
I think what we touched on right in the beginning is how actually really does it influence the surface? Under which conditions does it not influence the surface? Yeah, I think that's...
We would call it strat-trop coupling.
Yes, strat-trop.
Oh my God, what does that even mean?
Stratosphere, troposphere, coupling.
Oh,
Catchy.
You just can't be bothered to say the full words, can you?
What, you should have an acronym. That would make you know.
Yeah.
STC. Great.
Yeah, why not?
So investigating more the linkages between the stratosphere and the troposphere.
Yeah, and I think also how that might change with climate change, I think
totally.
is a crucial question that we don't really have a good answer for, and our models also don't have all the processes in them that they need. It's really expensive to have this ozone chemistry in a model, and so we mostly don't run with them. And so with the current ozone assessment that we're developing, this international panel is developing a state of our knowledge on the ozone hole. There's a new chapter on stratospheric aerosol injection, so geoengineering. And they're worried about the impact that if we do go to geoengineering and we start putting extra sulfate aerosols into the stratosphere to reflect that sunlight, to kind of buy us some time as we try and reduce greenhouse gases, that those aerosols could start destroying ozone again. But we don't have the models that can really actually understand that right now, that have all of these things at once.
And you mentioned that it's expensive. Do you mean computationally expensive? Like it takes a lot of computer power to run those models and simulations?
It does, yeah. So we do have some models, but we can't run them for very long, and we often don't run them with climate change at the same time, and so there's not much research on what geoengineering might do to some of these stratospheric processes.
So do we know less about the stratosphere than what we do about the troposphere, which is where most of the weather happens? Would that be true to say?
Yes.
Yeah.
Yeah, I think so. Yeah.
Is it any less important, the stratosphere?
Well, if you start playing with it, with this geoengineering, then, you're doing dangerous things. You have no idea. You're playing with something you don't know what it is.
Yeah.
Yeah, and that's kind of dangerous.
That reminds me of like when the cane toad was introduced to Australia to eat the dung beetle, and now we have a huge problem everywhere.
Yes.
You don't want to do that.
Yes.
Do you want to be the cane toad of the stratosphere?
I mean, the other thing is what Julie just mentioned is even our forecasting model don't change ozone. So if even if we're in a year where we have a larger than normal ozone hole, our forecast models don't know about that.
Yeah.
So there's definitely opportunities there to make things better, forecasts better.
So then, what's the future of research for the stratosphere?
Yeah, I think just this one is I think a big one.
Yeah.
Try to make put that changing ozone in somehow. And it's interesting because the world goes towards these very high resolution climate models.
Yeah.
But most of them pay for it by removing the stratosphere or making the stratosphere bad.
Bad.
We're not going to do that in 21st century weather, though.
No, of course not. No. We know better. We know better. But
that could be the centre's new tagline. 21st century weather, we know better.
Yeah, it
rhymes. Really get the public on side,
But yeah, we're, I guess, thinking of ways that we can incorporate some of these processes, but maybe not as expensively as doing the full chemistry. Yeah.
How serious are those geoengineering plans? Is it pie in the sky at the moment, or are there some crackpots out there in the US government, for example, who are like, let's do
it? Yes.
I think there's companies out there doing it already.
Yes.
Yeah, there was 2 20-something-year-olds I think Americans in Mexico who launched a rocket to try and do it and almost blew themselves up doing it. But so there can be some rogue players. I think it's getting more seriously discussed in the policy context as something we need to understand more about.
As an option, yeah.
There was a conference a couple of years ago, an international climate conference that a few people in the room attended as well. And one of the plenaries was about geoengineering and releasing aerosols into the atmosphere for global dimming. And I think quite a few were really uncomfortable hearing this talk. And I actually saw an article today as well that said that 1 in 10, only 1 in 10 climate scientists believe that geoengineering is a good fix anyway to climate change, let alone the problems that it'll have down the line.
Better off listening to the geoengineering scientists, then, aren't we?
I'm not taking that bait.
I guess one of the problems is as soon as you stop, should it become too expensive, or if you have a world war and nations don't care about that stratospheric thing anymore and don't put it up again, it jumps back right,
exactly,
as if you haven't done anything.
Exactly.
It jumps right back up.
It's literally a Band-Aid.
It's a Band-Aid, and there's also, you're messing with the winds and the state of the entire atmosphere.
Yeah.
So you're not just bringing it down cooler, but you're actually adding changes.
Yeah.
Which might be as bad as,
or worse,
even worse in some regions.
Yeah.
Than the greenhouse gas forcing in the beginning.
Julie's very sensibly put like an hour's time limit on the session, so we can all have dinner and have a rest. So I think it's Q&A time.
Yes. Oh, I forgot about this.
Can I borrow Zach for a second?
Sorry. Too busy talking.
So we have a handheld mic that people can run around the room with, and we will repeat the questions for the recording as well. Who has a question? Negan has a question. We'll just repeat the question. So Negan has asked, are billionaires blasting rockets into space and damaging the stratosphere?
Yeah, so there are real concerns that could be an artifact of this increased space travel, is that you will get more of particles in the stratosphere that then could accelerate ozone destruction again. And so again, we don't have much research on it yet, and we don't have many observations, but we need to be really studying this and making sure we're monitoring those effects and yelling at whoever needs to hear it if it is a...
Because of course it's not just billionaires on joyrides. We also do quite rely on satellites which need to be put into space. So, 100%. There is something of we've developed a necessity for space missions. So better do it sensibly. Sensible space.
Do it better.
Yeah, be better.
Does anyone else have a question about the stratosphere or anything else they'd like to ask Sarah, Martin and Julie? Lisa?
Yeah, happy to take it on. Thank you.
Would you
need to repeat the question?
Yes, I am repeating the question. So it's why we've always said there's more of them in the northern hemisphere than in the southern hemisphere, but we never explained why. Of them, meaning southern stratospheric warming. Yes.
Not rockets in space or asteroids.
No rockets, asteroids, or climate scientists. Well, there are
more
in the northern hemisphere. So, the big reason, back to the waves, right, which communicate the energy and everything. So where do these waves come from? And so most of them come from really large-scale, like global-scale perturbations, and that's the mountains. So you have the Tibetan Plateau in the Northern Hemisphere, we have the Rocky Mountains in the Northern Hemisphere, and also just land masses versus, so land-sea contrast, we call that.
Don't forget the Great Dividing Range, Martin.
Great Dividing Range. No, that's in the Southern Hemisphere.
Yeah, of course.
I'm talking about the Northern Hemisphere at
Yes,
the moment.
yeah.
And so all of these contrasts create more of these waves, and therefore you have much more chance that they become strong and actually disrupt the pole vortex. Where in the Southern Hemisphere, we have the Great Dividing Range.
Biggest, best mountains in the world.
May I just remind you that it was the British who named those?
Oh,
Yeah.
sorry.
So you should be. It's not nothing
I'll
great
resign.
about
So actually the one that do matter is the Andes.
Great, I'm going to have the podcast to myself.
Please go on.
So there is the Andes, but they're compared to what's there in the Northern Hemisphere, just not enough.
Yeah, we have a lot of ocean. And so there is some of these wave activity from storms in the Southern Ocean. They can propagate that. And yeah, some colleagues in the US have put in a new part of their model called moving mountains so that you can kind of get better approximation for how those storms might impact some of these big, large-scale things. But we just, as Martin said, the Southern Ocean is much flatter because the Southern Hemisphere is much flatter because it's mainly ocean.
And maybe also, this is why the ozone hole is also only over the Southern Hemisphere. So it's both, they're linked. So it's also warmer generally of the Northern Hemisphere because there's always these waves.
Oh, I didn't know that.
Does anyone else have a question? Greta, microphone's just coming to you.
So the question from Greta was understanding the role of polar stratospheric clouds on the ozone hole. And so it's because these cloud particles are kind of have more surfaces that these chemical reactions can occur on. And that's why it accelerates the ozone depletion. And so these polar stratospheric clouds form in the winter over Antarctica and in the Arctic as well. And that's why you get more ozone depletion in the Antarctic region compared to the Arctic, because the temperatures are so much colder and you get many more of these polar stratospheric clouds, I think.
Polar stratospheric clouds are really important because they bring all the ingredients together that you need for ozone depletion.
Thank you.
And that's it for this special live episode of Totally Cooked.
Many thanks to Julie, Martin, and our live audience for heading above the clouds with us, plus you at home.
And now it's back down to earth.
And so we'd like you to join us for future episodes of Totally Cooked to tackle many more interesting subjects.
That was not your line.
Well, I've realised... Okay.
That was not your
That's
line.
not the line, but you see, if we read it correctly, I fucked the line because...
You did, royally.
What normally happens is we'll then say, in future episodes we'll be doing this, and this, that's Sarah. And then I say for the answers to those questions and plenty more. But we haven't put any questions before the sentence. So
No, you're right. So did you just
I
do
badly
a copy and paste?
ad-libbed. Our copy and paste is our closest colleague in the engagement team. Pretend that never happened. Join us for the next episode of Totally Cooked.
And we'll tackle the climate crisis together.